In this notes lesson, I will be going over how to do electron configurations and a little background into quantum theory, which is super confusing. We are not going into very much depth with the quantum theory, so we're just kind of skimming the surface, but it'll help to have some background for electron configurations. So make sure you have your notes. We are on the bottom of page 4 of your notes with the definitions, section 5.1 and 5.2, electrons and atoms. And then you will also want your yellow periodic table packet. We are actually going to use second page, which is called the long periodic table. So this is the resource that you need. So if you need to pause the video to grab those, and make sure you grab something to drink, not to drink, to write with, but you can also have something to drink. I'm enjoying my coffee this morning. So here we go, electron configurations. Hopefully you look a little better than this on Monday. All right, so the quantum theory, this is the background. So you don't need to write this down, but just kind of, we'll go through it quick so you have a little better understanding. So Niels Bohr was a scientist that you may have heard of the Bohr's model of the atom. But one of his quotes was, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." So quantum theory basically states that in atoms, instead of, well, it's a mathematical equation. So here are a few of the equations that go along with quantum theory. Seems simple, right? So basically, quantum theory states that scientists can't determine exactly where an electron is located at any given time and how fast it's moving. It is all based on probability. So they can figure out where the electron should be at a given time, but not exactly where it's at. So kind of like, on Monday through Friday of most normal weeks, students should be in school from 8:30 to 3. So there would be a high probability that you would be in the school building during those hours. But you may have had to leave for an appointment, or maybe it's your day to stay home. So we can't tell exactly where that electron is, but it's all based on the probability of where it should be at any given time. So quantum theory, when we write electron configurations and we're writing all these weird numbers and symbols, basically it's an address for where we can find the electron. So if you are traveling internationally, you would probably tell someone that you're from the United States. If you are traveling to a sports tournament in Arizona, you would say that you're from Minnesota. If you met someone at the grocery store down the street, you might say that you live in a specific neighborhood. So all of these symbols that we're using for electron configurations are basically just is an address to where we can locate where that electron should be at one given time. So this is what the atom actually looks like. The darker concentrated areas are where the electron should be. That would be where it has a high probability of being, whereas the dimmer areas, it would be less likely to be, the electron would be less likely to be in that area. Okay, so now these are the rules that you're going to add to your notes on page 4. So that would be in your blue packet. So there's 3 rules that go along with electron configurations. We are really only going to focus on this first one, but we'll define all 3. So the Aufbau principle states that electrons fill lowest energy levels first. And once we do our example, I'll come back to these. Hund's rule states that electrons fill each orbital one at a time before pairing up. And Pauli's exclusion principle states that one orbital can hold up to 2 electrons with opposite spin. So go ahead and pause if you need to, so you get these definitions down. Really, the only one that's going to apply to us in our electron configurations is that very first one, the Aufbau principle. All right, so once you have those rules written down and are ready to move on, you can go ahead and flip to page 5 of your notes, where it has writing electron configurations for neutral atoms. Oops. So This document is in your yellow notes packet. It has the energy levels and sublevels. So I'm going to skip ahead and then come back. Energy levels are the numbers that are written on the left of each box. So 1s2, 2s2, 1s, 2s, 3s. The numbers that come in front are your energy levels. So if you remember, I'm going to try to write on here. Back in the day, you would draw the nucleus here, and then you would have that first ring around the atom where you would put 2 electrons, and then you would have that second ring around the atom, and possibly a third ring around the atom. So if you remember drawing atoms like this, where you put the electrons on these rings like it's orbiting, each ring represents an energy level. So the energy level represents how far those electrons are from the nucleus. So the higher the number, the farther the electron is from the nucleus. Whoops, I meant to erase that. All right, so going, back to the notes and then using your long periodic table. So the rules, and these are in your notes, you always have to start with hydrogen. So hydrogen has the lowest energy, which is that off-ball principle that you just wrote down. So you would always start with hydrogen, and then you read the periodic table from left to right, top to bottom, just like you would a book. So you'll always start with hydrogen. You'll increase in order of atomic number. That's probably the most important piece. So you'll go through atom of the atomic number 1, then 2, then 3, then 4. So you just keep progressing until you get to the element that you are writing the electron configuration for. The next step, part B, you will write the energy level first, which is a number, followed by the sublevel, which is a letter either S, P, D, or F. And these sublevels are labeled on your long periodic table in your yellow packet. And they're actually written right by the energy level. Then part C, you add the number of electrons as a superscript. So remember, superscript, super means, better than or on top. So superscripts are on top. And then you would repeat each step. So anytime you get to a new section on the long periodic table, then you would rewrite the energy level and sublevel. So if you were looking at oxygen, I'm going to go back to, we'll go back this way to just the plain periodic table. Okay, so oxygen is here. So if we were writing the electron configuration for oxygen, see how my writing is on this. You have to start with hydrogen. And again, you would start with your energy level and sublevel. So first we start with 1 and then S. When you count over in the 1s block, you count hydrogen and helium. So you would count 1, 2. So the number of elements that you count over is the subscript that you would add. So this gets us to helium. The next element is lithium. So you have to go in order of atomic number. We have to go 1, 2, 3, 4, and then 5, 6, 7, 8 to get to oxygen. So the next element would be lithium. Lithium starts with energy level 2, sublevel S. In the 2s orbital, or in the 2s sublevel, you have lithium and beryllium, so you have 2 elements in that sublevel. So again, you put a little 2. Beryllium is element number 4, so now you have to come all the way across here to element number 5, which is boron. Boron is in a new sublevel. So now again, you would rewrite the energy level. You would write the sublevel. So now we're in the 2p sublevel over here on the right. Oxygen is 1, 2, 3, 4 elements in. So the superscript that you add would be 4. So that's where you get the numbers and the symbols. So again, this gives us an address of where we should find the electrons for oxygen. It kind of tells you the shape of the path and how far it is from the nucleus. One other thing to point out is these superscripts. I'm going to switch colors here. So the superscripts, when you add those superscripts up, the sum of that should equal your atomic number. So oxygen has an atomic number of 8. 2 plus 2 is 4. 4 plus 4 is 8. So then you know that your electron configuration is correct.